Hi everybody, it's Jim Corkins. We are continuing on with our 7th lecture, and this one is about acceleration versus time graphs. Again, if you haven't done the reading, please start or please continue. The readings are noted in your Canvas modules. Thank you. All right, so we are looking at acceleration versus time graphs. There's a few things that you should know about it. First off, an acceleration versus time graph can tell you your acceleration at any given point in time. In what we had learned in a velocity versus time graph, that a velocity versus time graph will give you the acceleration at any instant in time, and an acceleration versus time graph will give you the acceleration at any given point in time. If you use the area underneath relative to the line of for an acceleration versus time graph relative to the zero line, you can actually figure out the total change in velocity. Now, that won't tell you which direction you're moving, okay? So just like the velocity versus time graphs doesn't tell you your position at any given point in time, an acceleration versus time graph doesn't tell you your exact velocity at any given point in time. It'll tell you your change in velocity at any given point in time, but it won't tell you your exact velocity. In order for you to figure out your exact velocity at some point in time, you would need an initial velocity, and then using this area, you can figure out the change in velocity, and then you could find out what your final velocity would be. So let's take a look at some acceleration versus time graphs and talk about that. So here we go. Again, if we take an acceleration versus time graph, and I'm going to note some times here. I'm going to call this 3 seconds. And I'm going to note this as 3 seconds. And I'm going to note this as 3 seconds. So the acceleration is happening in this acceleration versus time graph for a period of 3 seconds. Now this area right here is the change in velocity. Okay. And if we take this acceleration, so we're integrating a velocity, an acceleration versus time graph, and that'll tell us our change in velocity. So if we take that area, which is a rectangle, and we have negative 2 meters per second, velocity for every second, so that's the acceleration, times 3 seconds. I don't know why I changed that. I'll just keep it blue, times 3 seconds. Well, this little s is going to cancel out with that, and that's going to tell us our change in velocity, which is going to be negative 6 meters per second. Now again, this isn't telling us our exact velocity. All we know is our velocity is changing to the left. In other words, we're accelerating to the left. Okay? Now, if I gave you a starting velocity, you could use this change in velocity to figure out the final velocity, but that is not what is contained in an acceleration versus time graph. In this area right here, which is above the line, that change in velocity is going to be equal to a positive 2 meters per second for every second acceleration times 3 seconds. So again, this s cancels out with the s squared, or one of the s's in the s squared. And this is going to be a positive 6 meters per second change in your velocity. Okay. Now, this one's pretty easy since there is no acceleration here. I mean, I suppose we could run through that, but I mean, it's just going to be a 0 meters per second for every second acceleration times 3 seconds, which is, no surprise, 0 meters per second change in velocity. In other words, this acceleration is 0, which means you have a constant velocity. You could be standing still, which I guess is technically a constant velocity of 0. But you know for sure you have an acceleration that is 0. So again, every time we take the derivative of a velocity versus time graph, or a derivative of position versus time graph to a velocity versus time graph, we lose some information, like the specifics of your position. Well, when you take a derivative of a velocity versus time graph, you get an acceleration versus time graph, and now you lose the specifics of your actual velocities at those points. Well, let's practice what we just learned, okay? And in this problem, you're given a position versus time graph, velocity versus time graph, and acceleration versus time graph. But you're only given data for the velocity versus time graph, and you're told your starting position is -4 meters, okay? And what they're asking us to do is complete an acceleration versus time graph and a position versus time graph, given this initial position, and all of these variables, delta x, delta t, delta v, a, and construct these equations. Okay, and we could do some extra things there, but in order to do this, we are going to have to solve and use some math to solve some of this stuff. Okay, so we know for sure our initial position is -4 meters, so I'm going to put a dot here, and I'm going to mark it with a green guy. Okay. So we know our position, initial position is -4, and that's noted here. In the position versus time curve fit, that is -4 is our starting position. Okay, now let's look at our velocity versus time graph and try to fill in some of the blanks. It looks like our initial velocity is -8. Okay. So we know our initial velocity is -8, and we know our final velocity is +4. Well, let's figure out delta v here. We have oops, I forgot to make that a v. So we know our final velocity is +4 meters per second, or displacement of +4 meters for every 1 second. And then we're going to subtract from that a -8 meters for every 1 second. So that looks like the delta V is going to be 4 + 8, which is going to be a +12 meters per second change in velocity, which makes sense, right? -8, if you count by twos, 2, 4, 6, 8, 10, 12. So that's the rise. So we know this is a +12 displacement, +12 meters per second change in velocity. We also know right here the ending time is 4 seconds. Well, we could figure out the acceleration from that, right? In a velocity versus time graph, the slope is the acceleration. Okay, so the instantaneous acceleration here, this is a constant acceleration. So at any given point in time, the velocity is the same. So to calculate that acceleration, actually, I'm going to do it down here as well. Zoom out a little bit so we can make sure we're doing this. The acceleration, which is the sum of all these instantaneous velocities. Just gonna make sure I do this. So that's a positive 12 meters per second change in velocity over the period of 4 seconds. So I'm going to reduce this one. That is a positive 3 meters per second squared. So this is positive 3. Positive 3. And positive 3. If this was negative 3, I would put a negative. It's 1/2 times positive 3 times delta t squared. Okay. All right. Well, we have enough information to complete the acceleration versus time graph. We know it's got a constant acceleration of positive 3. So we are going to put that in right there, all the way across. Positive 3. And since we're here, we could use this area right here just to confirm that this positive 12 meters per second change in velocity is this area, just like we just learned. So this is going to be a positive 3 meters per second squared. Or a positive 3 meters per second for every second, change in velocity for every second, times 4 seconds. And that is going to work out to be seconds. This seconds cancels out with that. So we're going to have a positive 12 meters per second. So it works. Okay. Now let's construct our position versus time graph. And in order to do that, we need to figure out what the final velocity is. Because we have the initial position. We know the initial velocity at that initial position is going to be negative 8 meters per second. So the initial slope at this dot, this green dot, is going to be right here. Okay? So at that initial position is negative 4. All right. Well, we know its final slope, which will be a positive slope, which is the half as steep as this one we just gave it, is positive 4 meters per second. We just need to figure out where it landed. Now, the quickest and easiest way to do this is to just pop in our 4 seconds. That'll give us our final position right here. So let's do that. I'm going to try to color code this. And I'm going to zoom out a little bit so we could actually see the whole problem again. So this is going to be a positive 3 meters per second squared. And we're going to multiply this. Maybe I should zoom in a little bit. We forgot our 1/2. Our 1/2 is going to be in front of this. So it's 1/2 times positive 3. In fact, while I'm here, I'm just going to get rid of that and make it look a little bit better. I'm just going to call that positive 3, 3. And I'm going to put our 1/2 here. Little equal sign. Okay. Now we got to multiply that by 4 seconds that we're going to end up squaring. So we're going to square this 4 seconds. It's not 4 seconds squared. It's going to end up being 16 seconds squared. Now we're going to subtract from that this 8 meters per second times 4 seconds. And then we are going to subtract from that our starting position, which is negative 4. So our final position is going to be all of this. Let's figure that out. So this part right here is going to be 4 squared, which is going to be 16 times the 3 meters per second acceleration divided by 2. So that's 24. Now this is 8 times 4, which is 32. So we're going to subtract from that 32, which is -8. So I just did all of this. And now we have to subtract from that 4. -12. So overall displacement of this is going to be -12. Our overall final position is going to be -12 meters. Okay? So to figure out so we know at the 4 meter mark, it's going to be right here. I am kind of eyeballing this, but we know that's going to be its final position. So x final equals -12 meters. Okay. Is asking for the displacement. So let's figure out the total displacement here. We could have figured that out using the area here plus the area negative area here plus the positive area here. But let's just do it right here since we have it. -12 meters minus a -4 meters, which is going to be a +4 meters. You know what? I'm going to represent it this way. Yes, I know it's +4. I just want to make sure you have good notes, which is going to be negative, so that's negative plus 4, so that's going to be 8, -8 meters displacement. Which totally makes sense, because this is by 4s, so this is 4, and it's dropping by 1, 2. So that's, it works right there. Okay. Well, to create this last part of the graph, we found its final position. We know its velocity, its final velocity, which is its slope at that line, which is +4 meters per second. I don't like the way this looks. This looks too squished. And so this slope is, if that's 8, 4 has to be half as level. So I'm going to call that +4. That looks like about half of that. Well, to fill this in, it's going to probably look something like that, or pretty close to it. And so that is what that position versus time graph is going to look like. Okay? So this is all the information that we have right here. And that is how to construct using a velocity versus time graph and the information there and a starting position. We were able to construct an acceleration versus time graph, fill out all these variables, and construct a position versus time graph. And that's how all 3 of these graphs are related to each other, right? They all really do a good job at helping us out. Let's try another thing. Whoops, what is this doing here? Let's get rid of that. Where'd that guy come from? Okay, here is our acceleration versus time graph exercise, and this is the second one. It's giving us actually even more information. It says here we have a cart. It's got a starting position of +16. Right here, way up there. So we know its initial position is +16. Okay. And we know its starting velocity is +10. So its starting velocity is going to be positive 10. And so that means starting velocity is up here. Okay. It looks like it's giving us information from an acceleration versus time graph for a period of 4 seconds. So I'm going to put the 4 seconds right here. Okay. So we know quite a bit of information. I think we actually have more information than we did in the last graph. I don't know. We'll find out. We know the acceleration right here is going to be -2 meters per second squared over a period of 4 seconds. So it's going to be dropping, this velocity versus time graph is going to be dropping by 2 for every second. So we could actually figure out just from the graph and this information what our final velocity can be. But let's fill in the acceleration stuff right now. So we know the acceleration from that graph is -2 meters per second squared. So I'm going to just put a -2 here, a -2 here, and -2 here. Okay. All right. I absolutely do not know what to do. But we could figure out some stuff here. We know its starting velocity was positive 10. We're going to fill that in there. And we know its starting position is positive 16. All right. We've actually already figured out those two equations. Okay. Now, we could just use the graph, and I'm going to try this, and I'm going to double check it with math. Let's figure out what our final velocity is. Since we have we know this is going to be a straight line because this is a constant acceleration of -2, that means it's going to be dropping 2 for every 1 second. So it's going to be losing 2 meters per second for every 1 second. So starting at 10, we're going to drop to 8 for the first second, drop to 6 for the second, drop to 4 for the third second, and drop to 2 for the final second. So we estimating that it's going to look like this. It's a horrible line. I'm sure there's a way to make it straight. Oh, not going to worry about it. So I'm estimating the final velocity is going to be equal to that. But let's just make sure. Let's multiply in here a 4 seconds right here for here. So this is going to be 4 seconds times -2, which is going to be -8 plus 10. So that's going to be a positive, that's going to be a positive 2 meters per second. So it works. Awesome. All right. Now that we have that and we've constructed our velocity versus time graph, we know what its final velocity is. So let's just calculate that change in velocity again, which is going to be positive 2 meters per second minus a positive 10 meters per second, which is going to be -8 meters per second. And again, acceleration, that's going to be equal to the change in velocity divided by the change in time. So this is going to be, your change in velocity is -8 meters per second. And this is going to be 4 seconds. So we have an acceleration that is -2 meters per second squared. should be red. Okay. Another way to where we could figure it out, the change in velocity, is this area right here, right? So with that area, again, this isn't necessary to do it, but this delta V is going to be equal to the acceleration, which is -2 meters per second, squared for every second, 2 meters per second squared, times 4 seconds. Again, that little s cancels out with that one, and we end up with a total change in velocity of 4 times -2, which is -8 meters per second. So there, again, on these little exercises, there's a lot of ways to do these things. Okay, so since we know that change in velocity, it's right there. We just put it right there. Okay. Okay, well, since we started out using the graphs to figure out the change in velocity or the final velocity, let's use the equation to figure out the starting position of, the final position. We know the starting position is, again, x is +16. So let's figure that out. Let's figure out the final position. So we're going to put a 1/2 here. So this is going to be 1/2 times -2 meters per second. I'm going to try to color coordinate this, times a -2 meters per second squared times 4 seconds that we're going to end up squaring. This will end up being 16 again, plus 10 meters per second, plus a +10 meters per second, which is just 10 meters per second, times 4 seconds. And then we have our starting position, which is +16 meters. So this delta x is going to be, that's 16 times -2, so that's that'll be -16 plus 40, which will be 24. 24 plus 16 is going to be +40 meters. You know what? I'm just going to double check. 24 plus 16. Yeah, okay. Okay, so that means at the 4 second mark, it's going to be over here at +40. All right, and its slope is going to be much less steep. So this slope here at the +16 is +10. So let's do a really steep slope. And this slope later on is almost level. I'm going to zoom in a little bit so I could try to make this as accurate as I can. So I'm going to make this almost level. Again, our final position is +40. Oops, and I should have put a +40 displacement. No, our final position should have been this. Why did I put a delta x here? That should be confusing myself. Final position is +40. The displacement is going to be 24. Okay, sorry about that. So this is going to be 40 minus 16, so that's a positive 24 displacement. All right, our final velocity at that point is going to be positive 2 meters per second. And this is probably going to look something like that as it gradually comes to, as it kind of makes its way to be positive 2. So this is positive 10 slope. The initial position is right at 16. This is a positive 2 meters per second slope at that position, positive 40. Okay. So hopefully you learned a little bit about how acceleration versus time graphs interacts with velocity versus time graphs, and you could use those things to construct a position versus time graph. Now, here's the basics. An acceleration versus time graph is related to velocity versus time graphs, that the acceleration versus time graph is the slope in a velocity versus time graph. So notice that these two velocity versus time graphs are negative in slope. So that tells us that slope is a negative slope. This is a negative a as well. So which is going to give us a negative acceleration right here. Okay. Now, obviously, this is a positive velocity here. This is a positive velocity. And this is a negative velocity. That all those green data points are below that. So this would be speeding up and this would be slowing down. So that acceleration versus time graph doesn't tell you what your velocity is. It just tells you that you have an acceleration vector pointed to the left. Okay, similar to the concept of velocity is different from position. You just know the direction you're moving. You don't know your exact position. This is a positive acceleration. So you know you have an acceleration vector to the right. You also know in a velocity versus time graph that slope has to be positive. But again, this is a positive velocity because it's above the zero line. Since these velocities are below that zero line, those are going to be a negative velocity. So this is slowing down, this is speeding up. Over here, you have an acceleration that is equal to 0. There is no slope. So you know that this acceleration is equal to 0. And this is an acceleration that is equal to 0. You know that this object, whatever is causing this, is moving to the right. This one is moving to the left. So these are both constant velocities. Constant velocity moving to the right, constant velocity moving to the left. Slowing down, moving to the right. Speeding up, moving to the left. Speeding up, moving to the right. Slowing down, moving to the left. Okay, let's quiz you on this. We're only going to do 2 of these, and we'll do one last exercise, and then we'll be done. So, I want you to match velocity versus time graphs to acceleration versus time graph for this situation. You have a cart moving to the left, and it's slowing down while moving to the left. Match the velocity versus time graphs to the acceleration versus time graphs. Match letters to numbers. Go ahead and try it out and pause the video now. Okay, so we know it's going to have, if it's slowing down while moving to the left, okay, so we know its velocity vectors are going to be negative. And we know the acceleration vectors are going to be positive because it's slowing down, which means the velocity and acceleration vectors are pointing in opposite directions to each other. They're parallel, but they're in opposite directions. So which one of these acceleration versus time graphs shows a positive acceleration? Well, this is negative, this is 0, and this is positive. So we know 2 is correct. Okay, now from this graph, the slope here is 0. The slope here is negative. Nope, that's a positive slope. So that's a positive acceleration. This is a negative acceleration. This is a negative acceleration. And this is a positive acceleration. So it's got to be moving to the left, so it's got to be below the line. So C or E could match it, but we also need a positive slope. So C is a negative velocity, and it has a negative acceleration. E is also a negative group of velocities, but a positive acceleration. So E and 2 are matching. Let's try another one. Excuse me. You have a cart moving to the right and speeding up. So again, match velocity versus time graphs to the acceleration versus time graphs. Try this out. Pause the video now. Okay, we're back. Well, moving to the right, it's going to have a positive velocity in the x direction. And if it's speeding up, that means its acceleration vector, which is parallel to the velocity vector, is also pointing in the same direction. Okay. So number 1 shows a negative acceleration. Number 2 shows a positive acceleration. And number 3 shows a 0 acceleration. So number 2 fits this. Let's go with the slopes now. Here is a 0 slope. This is a positive slope. This is a negative slope. This is also a negative slope. And this is a positive slope. For velocities, this velocity is positive because it's above the 0 line. This velocity is also positive. These velocities are negative. These velocities are positive. And these velocities are negative. So we need positive velocity, positive acceleration, so B. So B and 2 fit this situation. Okay. Now let's move on to our last problem. And this is just putting everything together that you learned, specifically to a velocity versus time graph. So there's going to be, again, interpretation of a velocity versus time graph, constructing an acceleration versus time graph, but answering all these questions. Okay. So here we have a velocity versus time graph, which looks like it has 3 different types of motion. It looks like it has this first type of motion from 0 to 1 seconds, has a second type of motion from 1 to 2 seconds, a third type of motion from 2 to 4 seconds. So we're supposed to create linear fits for each one of those types of motion. It looks like we can calculate the acceleration for each one of those types of motions and then use that to put it on our acceleration versus time graph, and then start answering all these questions. So let's start trying this, okay? Here we go. So this first type of velocity, and it doesn't show the negative, and these are positive velocities, is it looks like it starts off with an initial velocity of 0. So the final velocity here is going to be equal to, and the slope of that line is 0 as well. So So that acceleration is equal to 0. So I'm going to put 0 meters per second squared times delta t plus 0 meters per second. All right. Now, from 1 to 2 seconds, it looks like, again, we're trying to predict final velocity. And it looks like our initial velocity, because it looks like it's not moving, nor is it accelerating. So this one's going to start off not moving. And let's figure out the acceleration just from the graph. Well, this is rising by 20 and it's only going over 1. So that acceleration is 20 divided by 20. Excuse me. Positive 20 meters per second squared. And then finally, from 2 to 4 seconds, now it looks like it's starting off at positive 20 meters per second. And let's figure out the acceleration of that one. It looks like it's a negative slope, so I'm just going to put a negative in front. And that is dropping by 20. That's dropping by 20 over the period of 2 seconds. So that's going to be negative 20 meters per, you know what? I'm going to negative 20 divided by 2, negative 10 meters per second squared. I'm just going to keep it like that, okay? Actually, you know what? You know that, okay, so this acceleration is going to be a positive 10 meters per second squared. And actually, I'm going to write this off to the side. You know what? I'm pretty sure you could just look down here. And I am going to call this negative 10. So let's just switch that to negative 10. Make it easier, right? We're going to need that for here anyways. So for the first second, it is not moving or accelerating. Now, for the next second, from 1 to 2 seconds, we have a positive 20 acceleration. And then it's dropping to 10, negative 10 acceleration over the period of 2 seconds. So this is what its acceleration versus time graph is going to look like. It's going to have this acceleration in the beginning, and then a positive 20 meters per second acceleration from 1 to 2 seconds, and then this acceleration from 2 to 3 seconds. Okay, there we go. Constructed it. Let's do this next part. We want to know the displacement from 0 to 2 seconds. So the total displacement from 0 to 2 seconds is the area underneath the line here, which is going to be 0. And then the area underneath the line right here. So I'm going to do this area right here. So this area right here is blue. I'm going to write a delta x here. All right. So to get that displacement, the very first area from 0 to 1 seconds is just 0 meters displacement. And then we're going to add this blue displacement, which is going to be, looks like we're 20 and over 1. So that's 20 times 1 divided by 2. So it's going to be positive 10. So the total displacement from 0 to 2 seconds is positive 10. Now the average velocity from 0 to 2 seconds is going to be displacement divided by time, which is going to be positive 10 divided by 2. So that'll be positive 5. The acceleration from 0 to 2 seconds, okay, so that acceleration, so we could do this a number of different ways. So let's do this. Let's just figure out the slope here. So that acceleration, so we're going from 0 to 2 seconds. So this change in velocity here over this period of 2 seconds, so this is going to be 10, 20. So that's, so when I think of A is equal to delta V over delta T, right? So this change in velocity from 0 to 2 seconds, which is this line right here, it's the slope of this line. So this is going to be it's going to be positive 20 meters per second minus 0 meters per second over that 2 seconds. Okay, so that acceleration is going to be positive 10 meters per second squared. So positive 10 meters per second squared. Now, what is the instantaneous velocity at 3? So they basically want to know what is the velocity at this point right here, which at the 3 second mark, we just take that line right over to there, which is 10. That is just positive 10 meters per second. We want the displacement from 0 to, I think they mean the displacement from 0 to 4 seconds here. So the total displacement from 0 to 4 seconds. All right, let's work with our velocity versus time graph. I'm probably going to have to erase all this. Okay. Maybe not, I don't know. And it's taking me forever to erase. Okay. Okay. So, total displacement from 0 to 4 seconds. So, that is just going to be the area underneath this entire thing. So, we already did the area here, which we found out is going to be positive 10 from 0 to 2 seconds. Right? Now we need the area for here, and we'll just add them together. So this area right here is going to be 20, so this is going to be 20 to 0 times 10. So that area is going to be 20 times 2 divided by 2, right? Because this is a rectangle, half of a rectangle is a triangle. So 20 times 2 divided by 2, so that's 40 divided by 2, so that's 20. So this is going to be positive. So this guy's area is going to be positive 20. And so to get that displacement from 0 to 4 seconds, and I should put meters there, we're going to take the positive 10 meters plus the positive 20 meters. So that is going to be 30. Now the velocity from 0 to 4 seconds is going to be displacement over time. Is going to be the change is going to be displacement over time. And what I'm saying is velocity is delta x over delta t. So that is going to be positive 30 divided by 4 meters per second. You could reduce that if you want. I'm not going to. So the average acceleration, which is the change in velocity, and I'll do this here, over change in time for the whole thing from beginning to end. So we started with a velocity of 0 and we ended up with a velocity of 0, right? So here's the starting velocity, here's the ending velocity, which is, this is weird, so 0 meters per second minus 0 meters per second over a period of 4 seconds, which is just 0 meters per second squared. So that's just 0. Okay. So again, this is how we construct acceleration versus time graphs. And I hope you learned a lot. Have a good day.